Let's talk about thermodynamics, the science of how heat moves and transforms into other forms of energy. Think about a cup of hot chocolate on a cold day. Why does it cool down? Heat always flows from hotter things to colder things until everything balances out. This simple rule is at the heart of thermodynamics and explains much of our technology, from engines to computers. Heat transfer is everywhere: boiling water, the sun warming the ocean, even your body keeping you warm. By understanding these rules, we design better homes, more efficient engines, and smarter technology. Thermodynamics connects the tiniest atoms to the largest stars through the language of energy. It's all about the laws that energy must obey no matter what. These laws help us predict everything from chemical reactions to weather patterns. By mastering them, we harness heat to make life easier and more efficient. That's the power of thermodynamics. Now let's see how heat moves, especially in liquids. First, conduction. Imagine a metal spoon in hot chocolate. The handle gets warm because heat travels from molecule to molecule like a chain reaction. But in liquids and gases, convection is even more powerful. Heat makes the bottom water rise as it becomes less dense while cooler water sinks, creating a circular flow. Conduction is heat transfer by direct contact, no movement of the material itself. Convection, on the other hand, is the movement of the fluid itself carrying heat along. Conduction happens in solids, liquids, and gases, but convection only happens in fluids. When you see water bubbling or feel warm air rising, that's convection in action. Stirring your hot chocolate, you're speeding up convection, mixing hot and cool parts faster. Both conduction and convection work together to move heat in balanced temperatures. They're the dynamic duo of heat transfer. Next, let's see how we keep track of all these changes. So, how do scientists track all these changes in heat, temperature, and pressure? Enter the Mollier Diagram, a map for energy. Instead of roads, it shows properties like enthalpy, total heat content, and entropy, measure of disorder. Enthalpy is on the y-axis, entropy on the x-axis, making it easy to visualize what's happening inside a substance. The diagram is covered with lines for constant pressure, temperature, and steam quality. You can follow a path on the chart as water heats up and turns to steam, seeing exactly how much energy is added. It turns complex equations into a visual journey. Engineers use it as a shortcut to find the information they need, no endless calculations. The Mollier Diagram is a GPS for navigating the world of heat energy. Let's see how it's used in real engineering. Engineers love the Mollier Diagram because it makes designing things like steam turbines much easier. For a turbine, you start with high-pressure steam and trace its path as it expands and loses pressure. The ideal process is a straight vertical line, constant entropy, showing maximum efficiency. Real-world inefficiencies make the path slope, revealing where energy is lost. By comparing the ideal and actual paths, engineers can improve designs, maybe by tweaking blade shapes or materials. The diagram isn't just for turbines, it's used for boilers, condensers, compressors, and evaporators in refrigeration and air conditioning. It helps track energy and properties throughout the cycle, optimizing for power, efficiency, and reliability. The Mollier Diagram is a cornerstone of practical thermodynamics. Now let's see it in action in your kitchen. Here's how it keeps your food fresh. Your refrigerator is a heat pump, moving heat from inside to outside using a refrigerant. The Mollier Diagram helps engineers design fridges to absorb and release heat efficiently. Inside, low-pressure refrigerant evaporates, absorbing heat and cooling your food. On the diagram, this is where enthalpy increases as liquid turns to gas. The compressor then raises the pressure and temperature, traceable on the chart. Hot refrigerant releases heat outside and condenses back to liquid. An expansion valve drops the pressure, cooling the refrigerant for the next cycle. Each step, evaporation, compression, condensation, expansion, can be plotted and optimized on the Mollier Diagram. This science keeps your food fresh and your home comfortable. Thermodynamics isn't just theory, it's science you use every day.